Let's start out with some logistics. First of all, take your homework, pass it in. Homework passed in yesterday. Good. I'll have the homework that's due Thursday posted by Wednesday night at 10 o'clock. Well, I want to give you plenty of time to do it, and I know you're going to be up till 4. So, okay, there's no homework due Thursday. There's only, after today, 3 lectures. 1, 2, 4 lectures left. One of them I'm not going to be here for again, which is this Thursday. So you have a structural mechanics introduction by the guy who usually teaches this course. So the guy who's going to lecture on Thursday is the guy who's taught this class many times. How were the lectures on last week? Both of them good? Very good. And the homework that was assigned? Good. Professor Marjolijn told me, Vandermeulen, that she was disappointed that you did not know the Young's modulus of either steel or 200 what? Gigapascals. I think I said 2 gigapascals in lecture. Sounds wrong. It's only a factor of 100. Okay. You guys are supposed to have cars working by Friday. We're giving a slight extension. So by the end of the weekend, you have to have shown one of your TAs a working car. It does not have to be your TA. Over the weekend, there are various TAs that are going to be in. So either this week sometime or over the weekend, make sure you show it to them. Make sure they've written down your name, your group name, and written down a comment about your car. I'm going to assign one more homework assignment for the whole semester. It will just be a slight extension of what we've been doing so far. I think some of you are drowning in MATLAB, so I just want you to catch up with what we have so far. Last, there's no prelims in this class, no final exam. I only had 1 quiz so far. We're going to have another quiz, and I think we're just going to do it on the last day of classes. So there will be an in-class quiz, the last day of classes. It covers everything for the whole course. So it will be a final exam, basically, in class Thursday. It covers all MATLAB, all car, all steel, all floating ice, all everything. I will try to make it a not time pressure test. So even though it's only 50 minutes, I'll try to make it simple questions about things we've had this semester. Any questions about the logistics for the course? Yes?
Will the quiz include everything we've learned or just what we've learned after the quiz?
Everything you've learned from day 1 to the end. Okay? Any other questions about the logistics? Yes?
The material from our materials from the labs.
Labs, yes. Everything. Everything. Any other questions?
You said 4 lectures after today?
There's this Thursday, next Tuesday before Thanksgiving. After Thanksgiving, there's Tuesday, and then there's Thursday. That's 4. One of them is going to get used up by a guest lecture on Thursday. One of them is going to get used up by the final quiz, so there's only 2 more lectures. Yes?
So
By me.
The quiz will be on the Thursday, our last Thursday.
The final quiz will be
You said the last day of class.
our last day of classes, which is the day before what you think of as the last day of classes, which is Friday, which is 2 days before the actual last day of classes, which is Saturday, even though you never have classes Saturday. Does that answer your question? Okay, so the final homework will be Tuesday after Thanksgiving. It won't be due next week. And as I said, it will just be a slight extension of the stuff you're doing already. Let me get the computer to work. So the homework that was due yesterday was, I think, judging by office hours, people found it somewhat difficult. So I'm going to go over some maybe more advanced ways of dealing with that homework in lecture today. So my main topic today is just to address the homework you had due yesterday. So let's just start out with a vote of some kind. Okay, ready? You got a question you want to ask the class? Any questions anybody has for the class? Anybody want to make a point by showing everybody thinks such and such? And we'll make that the poll question. What is my question? My question to you is, do you have a question that you would like to ask the class? No? Okay, let's start with this. Homework that was due yesterday. If I gave you 8 hours to do it on your own right this minute, you could do it. If I gave you 8 hours to do it with a friend, you could do it. You found the whole thing. You answer the most advanced one, which applies. If I gave you 8 hours to do it with a friend, you would struggle. And if I gave you 24 hours to do it with whoever you wanted, you still wouldn't know what you were doing. Okay, so we'd like to push this thing in this direction, and that's the purpose of the last homework. Of course, if you're totally floundering and you don't know what you're doing, you have to ask for help, and you're limited for time, and so I realize that you can't get through everything. But you'd like to try to get through it. The goal for my course is for you to have this MacGyver attitude. I keep saying MacGyver. You understand what I'm talking about when I say MacGyver attitude? Yes? You don't know what I'm talking about when I say MacGyver attitude? No?
Do you understand MacGyver attitude?
Okay, so that's the goal, which means you should, if I've been successful, have taken MATLAB out and used it for other courses. Checked your math homework with it or something like that. And I would suggest over Thanksgiving that just you play around with it. Just get it, just play around. You can't, if you want to get good at it, you can't do it by memorizing syntax. You can't get it by looking at somebody else's code. You have to be in there making your own mistakes over and over again. To like you have your attitude about everything, like when you're building your car and all your engineering homework and so on. But MATLAB is just the one place that we've been emphasizing at this semester. Okay, I want to start out. I guess I've got to register this vote. I want to start out with the last homework problem, which was differential equations, which is this block of code here. Can everybody see the board? Okay, now I'd like you to challenge yourself to ask a question if something is unclear. This is going to be by far the easiest part of this lecture, and it's going to get much more confusing when I get to the other homework problem. Okay, we're going to try to solve a differential equation. We're going to put the differential equation in a block of code like this, which says, give me a list of numbers, and I will tell you the rate of change of that list of numbers. And that's the way we think of as differential equations, crystal balls. They're equations that predict the future from the present. You tell me the present state. It tells you the rate of change of the variables. Then a solver marches forward in time using that information. We're going to think of the list of three variables here as being x, y, and z, which we unpack just so it's easier to read the rest of the program. Then we're going to have some parameters that are going to describe the differential equation. Everything after the percent you could ignore. Those are just numbers to remind me of things to try. And I'm going to have these three parameters, 10, 8/3, and 5. Those three parameters turn out to work good for my example. Now I'll have my differential equation. The rate of change of x depends on x, y, and z. Well, actually, it only depends on y and z. The rate of change of y depends on x, y, and z. And the rate of change of z depends on x, y, and z. Three simple-looking functions. So you can put whatever functions you want in here, and that's what you're supposed to play with. Guess what's your question?
What is the x equals z equality?
what's this about? Okay, ZZ is a list of 3 numbers. And according to the syntax of the differential equation solver that we're going to put up here, we have to write a function that when we put in 3 numbers, spits out 3 other numbers, which is the rate of change of those numbers. So all I need to do is make sure that I have at the end a line that says z dot equals, and then 3 numbers in here. The way I'm going to go about doing that is I'm going to think of those 3 numbers as x, y, and z. Since I'm going to think of them as x, y, and z, I might as well call them x, y, and z, and that's what this line is about. That way, when I calculate, I can think of x, y, and z, and the rate of change of x, y, and z, and those actually are the rate of change of z1, the rate of change of z2, and the rate of change of z3. Does that address your question? Yes?
Could you do, say, y dot as a function of x dot?
That would be breaking the crystal ball rules. Crystal ball rule says I can tell you the future from the present. So the right-hand side of the equation, you only have to have the current state. You can't have the rate of change in the current state. Now, in these equations, I could put x dot over here. It wouldn't break the computer. It would break the computer if I put y dot up here, but it wouldn't if I put x dot down here, because then we're calculating. But it breaks the philosophy of these equations. Given the present, you want to look at the future. So the rate of change of the state on the left-hand side, the current state on the right-hand side. Is that a question? Yes? Yeah, there is a reason I call it ZZ. I have been calling it Z in the past to represent the list of numbers, but now one of the numbers I want to call is Z. I think that's why it's Z coordinates. So I call it ZZ to distinguish it from Z. And in fact, when I was writing this for class, I called it Z. It got an error because I had these 2 different things. Does that answer your question? In lecture, when you use the same variable to mean 2 different things, students get confused. The computer programs, either you get an error or a wrong answer. Okay, so now we're going to run this thing. We have to put in initial conditions. Let's put in simple initial conditions to start with. And as a debugging rule, if you have a program that's kind of general purpose, don't give it a hard time right at the beginning, because you don't want it to waste time when all you're doing is looking for syntax errors. Let's give it a simple initial condition and just a small amount of time to run. Here's the big command for solving differential equations. You put if the command is ODE23, or you can type here ODE45. Functionally, it's the same from your point of view. It's just slightly different accuracy. Here's the name of the differential equation with an @ sign in front, meaning that the function is somewhere here on the outside. Here's the t-span, and here's the initial conditions. Then I'm going to unpack it here. This is just so I can think about these variables and not type them in a confused way. That's sort of the analog of this thing down here, where I unpacked it in the differential equation. And then I'm going to plot them. What I asked you to do was make a plot of x, y, but there's actually an x, y, and z, so we could plot the curve in 3 dimensions. X, y are parametrically described by time, but we're just looking at the trajectory. So we could put it in a 3-dimensional plot. If you want to look at both plots at one time, you can use the subplot command. Anybody discovered the subplot command here yet on their own? Raise your hand. Okay, the subplot command is a way of putting 2 plots, have them spit out at once and arranged nicely, so you don't have the windows all tangled on top of each other if you have multiple plots, or don't have the rewriting. It says make a 2x1 grid of plots. That's 2 plots, one on top of each other. I could have a 2x2 grid and make the first plot and then do normal plotting with it, and then make the second plot here and do normal plotting with it. Who wants to talk to me on Skype? Should I talk to them now? I think I need that. So I have these 2 plots. Now I can run this thing and see what I get. So I look at the back is the function f5, and I have these 2 plots, one on top of each other. One's a 3D plot, and the plot is, well, right there, it says teeny dot there, and there's a teeny dot there. Now why is that? I put an initial condition of 0, 0, 0. Down here I have the rate of change of x. Well, oops, it's going to be 0, it's going to be 0, it's going to be 0. It can never get away from 0. Because I have 0 to start with, it just sticks at 0. It's like taking exponential growth and putting an initial condition of 0, you don't get anywhere. Okay, so I'm not going to get anywhere unless I put in some decent initial value here to at least get this to take off. So I get it to take off, and I run it again, and I get some curve. And this is what, well, see now, these values aren't changing by very much. In fact, the z value here, look how little is changing in this 3D plot. See, z dot is x times y, b times z. Nothing much has happened. There's a y that starts at 0 and z that starts at 0. They haven't had time to take off. And not much has happened time-wise. So let's just run this for a little longer in time and see what we get. And it starts to look more interesting. Run it longer in time to see if it looks more interesting. Oh, it looks like a spiral again. Run it longer in time and see if it looks interesting. It doesn't get any more interesting. So it looks like it spirals in to a little dot here, somewhere in three-dimensional space. And when it gets to that little dot, that's going to be a value probably where y is going to be equal to x. So probably this point here is y is equal to x because it just went there and stopped. So let's just see, y equal x, 3.2, 3.2, yup, it looks like it does. So it went to a point where the right-hand side came to a stop. It didn't go any further. So you got the same answer for 10 as 100. Any questions about this? Okay, so that's a little bit of an interesting plot. Let's just try putting in some other numbers here, like, oh, let's say 28. And then running this again and see what we get. And we get something pretty. And if we put a longer time here, it actually gets uglier because it just overwrites on itself too many times. Function F5. But if we want to see, it's just written on top, so if we have to make a big plot if we want it to look really pretty. If we want to sort of see more what's going on here, we can put 20 in here. What's happening is it starts someplace, and then all the interesting stuff it takes a while for it to find an interesting part of the world. Maybe I should put a bigger, interesting part of the world is up there more, so maybe I should put a bigger visual condition in that starts near the interesting part of the world. Run it again. Not long enough. Run it again. Went to some boring place this time. This. So we start at different places, it does different things. Okay. This happens to be a famous set of equations. It's all right in here in this crystal ball. It's rules for evolving the future from the present. In this case, there's 3 variables. When we started this course, we just did 1, first-order differential equations, of which integration or calculus is a special case. Then we did 2, like position and velocity. But now we did 3, x, y, and z. And there's some rules that are predicting the future from the present. Now it turns out these rules here were intended to be rules for simple rules describing the motion of the air in the atmosphere. Very simple rules for the air in the atmosphere. Very simple model by a guy named Lorentz, I think in the 1960s. And he went and plugged this model into the computer and got this weird result. And this is the first famous case of a discovery of chaos in the modern era. So some few people knew about this in about 1900 by some kind of abstract thinking, but this was a case where somebody went on the computer, figured out that simple equations can give complicated chaotic solutions. And you can look at this and see it has so-called sensitive dependence on initial conditions, and the solutions are really wild and so on. So this is what's it take on the computer to see this? This is all stuff which at this point you know. Simple equations, complicated outputs. Can you write this output in calculus with sines and cosines and so on? No, you can't. No, neither can Ramanujan. Nor any of your professors, nor any professor in the future. It's an essentially numerical result, or we say an abstract result. It's about functions, but not about functions that you can write in algebraic form. Any questions about this? Yes? I can't hear a word that you're saying.
Is the z naught equal to what's the
Is that the same as what?
I'd rather just 2 z naught equal.
Oh, that's pretty good. here says z dot, here says z dot. It replaces this z dot with that z dot, which is just the thing I needed up here. So here's a case where I got away with confusing the lecture and the computer thought about it the right way. So I meant that. But it worked out to my advantage, even though I typed it wrong. Okay, any other questions? Yes?
Why is there a apostrophe after
This is a detail of MATLAB syntax, and it wants this as a column vector. And this takes this list of these row things, puts it in a column. The other way to do it would be to put semicolons before this and leave that one out. Other questions? Okay, did anybody manage to find a picture that they thought was pretty? Raise your hand if you got a pretty, what you get? What?
It's not pretty even. It looks like a whale.
Like a what?
A whale.
A whale. So you got complicated squiggles? Did they were they periodic or were they chaotic, you think? So the relatively easy thing to do is get things like Lissajous figures, which are like ellipses that are slowly rotating. Those are pretty, and they are not that chaotic. Okay, I want to drop this and move on to other things. No more questions on this? I think it's cool that, you know, look at what's in this MATLAB code. It's nothing that mysterious, and it gives you this chaos. Here you are, a freshman in college studying chaos. Can I email you this program? Yes. I'll just have it posted. It'll go next to the lecture video posted. Those of you who are talking to each other, do you want to say something out loud? You please do. Comment or question? Okay, now I want to go back to the car. I've been trying to make this car example both somewhat representative of mechanical engineering and relevant to your project. It's a fact of these projects, these student projects, that it is very hard to make yourself think in a school-like way when you're building something. When you're building something, it's part of human nature. You would rather spend 4 hours filing something and try it than you would to spend 10 minutes doing arithmetic to see whether you actually want it smaller, bigger, heavier, lighter, whatever it is. I don't know why it is, but this is just a fact of human nature, and we're almost all subject to it. I find myself doing the same thing. I'll just do something really tedious for a long time to avoid doing some simple arithmetic. Nonetheless, I've been trying to teach you things, have you practice things which are relevant to this project. That is, I believe it's possible that by doing calculations of the type I've been showing you, you can make your car go faster. Not only that, I believe that even without doing calculations, if you're paying attention to what we've been doing, it will give you intuitions that will tell you things to look out for that might make your car go faster. Now I just want to continue with both the intuitions and the details as far as this goes here. So one thing is we have this idea that we have a motor, and the motor has some properties. And then we have the car, and the car has some properties. And the car has this motor on board, but what we're interested in is the force down here at the wheels of the car and the velocity of the car. This is not quite a free body diagram. And with the motor, we have some torque, and we have some angular velocity. And the motor has some properties. And you've measured the properties of a motor. Your motor did not actually follow quite the ideal motor, but it gave you a sense of what an ideal motor would be like. Usually the ideal motor, people assume, goes like this. My recollection is that your motor in the test had trouble down here at the low speed ends. It sort of died out and just wouldn't do anything when the speed got small. And this is because of something about the electrical contacts inside it. There's a little dead, it's a cheap motor, and there's little dead spots, and it gets stalled out by electrical contact not being made. Nonetheless, we have this motor which has this various parameters which describe the motor. It applies a lot of torque when it's not moving fast, assuming it's making electrical contact, or at least it applies a lot of torque when it's moving pretty slow. it can only go so fast, even when you're applying no torque to it. We could extend this line down here, and then this would not be about motors, it would be about generators. The same thing that works as a motor is that works down here. When you move it faster than it would naturally go, and it pumps electricity the other direction. And this, by the way, is for a fixed electrical supply. So we could say for a fixed battery, we could say for a fixed voltage. Then associated with this curve, we can draw a slope here of c, and c is then the ratio of m0 to this free spinning velocity. And we can also pick out here the peak power, which is the area, which is the maximum power we can get from this. And this peak power is equal to m0 times this omega free divided by 4. So we have four numbers which characterize this number. This m0, this omega free, this c, or this peak power. And any two of these determine the other four. And there are different times when you want to think about a motor different ways. Most often, the most essential thing you're interested in is this peak power. Now, why is that the most essential thing? Is that given the peak power, we can draw lots of motors that have that same peak power, but we can get any one of those motors from the other by adding a gearbox. So the stall torque is important once you have a motor and a gearbox, but if you are going to design the gearbox, which is the little gears, or the radius of the wheels, or the size of the pulleys, or whatever it is that you're going to use for your transmission, and you're going to think of that gearbox as being conservative, not dissipative, not wasting energy, that has the same energy and is coming out, then you can move these 2 points in any way which is consistent with keeping this peak power the same. So there's a set of points here, which are the set of points which all have the same peak power, and we can get to a curve that has a tangent point, a motor line that has a tangent point on any point on this curve by changing the gearbox. And if you have what's a big gear reduction, what I call a big G, big gear reduction, then the moment goes up by a factor of 2, and the fastest speed goes down by a factor of 2, and we're getting a curve like this with a tangent gear. Is that clear? Now, when you go and put this motor on a car, what we're going to get out is the drive force in the car, and if the car is going to have some speed, there's going to be some speed of the wheels. And these have different units than this on the motor torque and motor angular velocity, but somehow it's a reflection of the same idea, because the gear train, which includes the gears, it includes any pulleys, it includes the radius of the drive wheel that's touching the ground, tell us how to get from here to here. And so similarly, we will have a curve for the car as a whole, which will have in it some stall torque, some free velocity, how fast the wheel spins when it's free. It will have some curve here, which I'll call C prime, which will tell us the relationship, and it will have some peak power, which will be this area under this curve. So once you've built the car, you can test the wheels and draw the same curve as you could for the motor as a whole by just looking at the force and the velocity of the wheels. Now these two curves are related to each other. How are they related to each other? Well, this F0 comes from this M0, and then we have what we call the gear reduction, which says how much have we slowed down the motor, and we call that the G, and when you slow down the motor, you get a bigger force. So this is the relationship between the F0 and the G. On the other hand, we have this VF down here, and this VF is this omega free divided by G. And this is this a key idea that whenever you amplify force, you attenuate motion. Whenever you amplify motion, you attenuate force. The way I've been defining gear ratio is a gear reduction, which makes the motion small. We're measuring how much we're making the motion smaller. Therefore, we're making the force big. In a big gear ratio, you have a big force. Big gear ratio. Now, there's a little confusion in the words, which I pointed out before, is when G is big, there's a big gear reduction. That's called a low gear on a car or a bicycle, because you go slow for a given engine speed, or a given pedaling speed. Everything clear so far? Now, if we assume that the transmission has no energy losses, the peak power is equal to peak power. And you can see that by saying the peak power is half the peak force times half the peak velocity, which is like half the omega and half the m. But one of these increases by a factor of g, the other decreases by a factor of g, so the area here is the same. So everything is consistent as far as the energy balance and the force matching. And that's why you have in gearboxes that when the force gets bigger, the motion gets smaller. It's because it has to balance energy. At least that's one way to think about it. Okay, well this C prime we can also get from F0 and VF is F0 over VF. So we could just characterize the net effect of our car transmission by saying the car has the property, so now we're going to look at the car, and the property for a fixed so-called gear ratio is that it's got some F0 minus this C prime V, but this C prime we said is F0 over V sub 3 times V. But if we're going to characterize things in a simple way, we're going to say that the motor has some power. So since the motor has some power, some peak power, that peak power is F0 times V sub 3 divided by 4. That means we can solve for V sub 3 in terms of the peak power. It's the peak power divided by F0 times 4. So that means we can write that the force is equal to F0 minus, and we make this substitution in here, and we have an F0 squared, where we have this F0 divided by F0t, so we have an F0 squared divided by 4t times t. So given the power of the motor, we can sort of characterize the gear ratio by what is, for that gear ratio, what's the maximum force it can apply with the motor is stalled. Okay, so in the plot you had yesterday, you had to pick an M0, but all that showed up in the equations was M0 times G. What is that? That's the force when the motor is stalled at the wheels. So when you parameterize things, all that showed up was that quantity. So if you picked an M0 and you solve for things in terms of the gear ratio, really, if you would have picked a different M0, you would have got a different G, but the product would have been a mix. So all that's showing up is this quantity. Okay. Questions so far? Yes? How did I get this first one? I looked over at this graph, which maybe you can't see. Is that the problem? People? Here is this relationship between the force at the wheel and the speed of the car. How do I know it's a curve like this? Because I know the motor stalled at one point, and I know it can only go so fast. So this has some slope like this. Then what's the relationship between this C prime and these two quantities? Well, it's just rise over run backwards. Run, fall over run. Okay. Rise over backwards run. Okay. So anyway, this is a slope here, and we know this peak power is half this height times half this width. So address your question or no? Where did I get this from? Where did I get that one from? I got it because I got it by staring at that picture and knowing it has to be correct. You want to know if I want to try and be all algebraic about it, I would have to start out with this equation, n is equal to m0 minus c omega. I'd have to find the relationship between m0 and f0. I'd have to find the relationship between omega and v, all from the gear ratios, and I'd end up over there. But I just know the graph has to work out like that. Yes, no? Scratching your head,
Just a
question?
if we multiply that expression by g,
Remember, there's a g that goes upstairs and downstairs.
so that omega,
This one goes up by g, this one goes down by g.
so shouldn't the new constant be c times g squared or something, or c by g squared?
It ends up with an m0 squared g squared over here. Sorry, over here.
Okay.
Okay. Now, your experience if you drive a car or if you ride a bike, either one, and you want to start from stop and you want to get up to some speed or you want to go some distance, if you're in too low a gear, on your bike, too low a gear means too high a G in this thinking here, too much of a gear reduction, which means the engine spins fast for a little car motion. If you're in too low a gear, you don't get to where you want to go very fast because, why not? The engine only goes so fast, and either you're spinning your pedals or the engine's going and the car is just not going so fast. If you have too big a gear ratio, the car doesn't get from here to there very quickly. On the other hand, if you're in too high a gear, this corresponds to a small g, too small of a reduction in the motion, then you have too small a force at the wheel, and what happens is you go to push on the pedal, and you push on the pedal, and it feels like nothing's happening, and very, very slowly you build up speed as the pedal goes slow, and you don't get from here to there very fast because there's small force on the wheel. And on the car, it's called lugging, and the engine will stall. You try to start in third gear, and if you succeed, which you might, let's say you're already moving a little bit, and you barely accelerate. So there's a right gear for getting from here to there at the best speed. Now actually, there's not really a best gear from going from stop up to 65 miles an hour. If you're stuck with a fixed gear, there's some gear that's going to be best. But there's not really best gear. At each speed that the car is going, you would like, or the bike, you would like to get access to this point here. So what you want to do is always change your gear ratio so that you're operating on this point as far as the motor is concerned, and you're operating on this point, and it matches this point here. So how do you have to do that? Is you have to keep changing this curve, and you change this curve by changing gears, so that the midpoint of the curve drops down to the speed at which you're presently going. So if you have a big gear reduction, you'll have a small motion, you'll have a big force, and you'll have a big steep curve like this, and that will give you a big force and lots of power. On the other hand, if you are going fast, you want to change the gear reduction so you're operating over the peak power for that speed. This is why, when you're riding a bike, you change gears as you go faster and faster. You want to keep the motor here, which means you have to keep shifting this curve, keep the midpoint of it near your current operating speed. Now in your car, as most of you are designing it, not all of you, you are stuck with a single gear, and you have to pick the one which on average somehow does the best job for you. Is that clear? Now you want to figure out which one it is on average, and you have to do this calculation, which I don't have time to talk through in detail, and I'm a little afraid to send it out to you. But I'd like to just quickly talk it through so you can see a sort of mode of thought for dealing with these complicated calculations. And the mode of thought is the following. Once you know how to solve a problem, take that as given and say, I know how to do that one, and then move on and solve in terms of what you know already. So you don't say reduce it to a problem you already know how to solve. But once you've done that, you can do a new problem, and you take that as something given, and you keep moving your way up. Now you can do the same thing in computer programming. Is once you know how to do something, encapsulate that, and then move on to the next level. And the way to do that, sort of the syntax way of doing that in MATLAB is with functions. And we put together now enough pieces so that you can do a pretty sophisticated encapsulation if you trust yourself enough to use the steps that you've already understood. So let me start out with a car example here. Here's a car like the one you did on the homework. And I've now added a little bit of complexity in the syntax. I could have avoided this, but I'm going to teach you some new syntax as well. So here I have my right-hand side, but I'm also going to pass in parameters. So this allows us to pass parameters into the differential equation solution. And now here I'm going to say my x dot is equal to my velocity, and my rate of change of velocity is the propulsive force minus the drag force divided by the mass. Well, that parameter here includes a bunch of things, which are called p dot m and p dot this and p dot that. So it's a MATLAB syntax that you can label variables x dot a, x dot b, x dot c, and you say what's x? X is that list of things, x dot a, x dot b, x dot c. So I don't know if the technical word for it is a structure. You know what it's called? Is that called a structure? It's a collect what? A struct. A struct. It's called a struct. But it's a way of hiding lots of information to one variable. It's a little more general than these vectors and lists of numbers because they have names. Okay, so I'm going to say that the drag force is this p dot cd, the coefficient of drag times the area times the density times v squared over 2. You didn't have that in the homework, but we did that previously, an air drag force. We could have added another drag force for friction, probably more relevant for your cars would be a constant force representing the friction of all your bearings, and a propulsive force from the motor, which is just that. This is just that propulsive force we just calculated from the formula over there with the constants filled in terms of F0 and the tower. Somewhere upstairs we're going to have to say what all these constants are, but we're going to use them in a kind of complicated way. So here is this way of finding the motion of a car versus time. Now I want to do a calculation, which is I'd like to calculate how far the car goes. And I'm going to call it how far as a function of the time and the gear ratio, which I'm going to characterize by the stall force. So I'm going to put in all these parameters. I'm going to get ready to pass them to the differential equation. And passing the differential equation is done with this little syntax twist here. You put a square bracket followed by p, and that passes parameters into the differential equation. And then I'm going to solve the differential equation, and I'm going to say the distance is gone is the last value of x. So now I've used my ability to solve differential equations to calculate the total distance in terms of the total time and the gear ratio. So now I can encapsulate that whole knowledge into just this command here. You give me a time and a gear ratio, and I'll tell you how long it takes to go some distance, assuming all the other constants are fixed, the power of the motor, coefficient of drag, and so on. Now I can make a new function, which is called error. And this function is, I'm going to take the time, I'm going to take the gear ratio, I'm going to take a desired distance, and I'm going to find out how far the car went compared to how far I wanted it to go in that time. I'm going to call this error. My error is this error. Well, now that I've got this error, I want that error to be 0, because my goal is, given a distance and a gear ratio, I want to figure out how long it takes. So I want to keep making guesses on this time to make this error 0. That's called root finding. But we did root finding a month ago. So I want to do root finding on this function, which is this error function. It's not the error function like e to the minus x squared. It's the error, how far we go compared to how far we wanted to go in a given time. And so I use the syntax of this root solver, which I believe I showed you. Correct that I showed this to you? I have it on my computer as if I showed it to you. Is it correct that I did? You had it on homework, fsolve, didn't you?
Yeah.
Okay, so you've seen fsolve. So I call the fsolve command with this weird complicated syntax, which you learn better from Google than you do from the MATLAB help. And it says, given this desired distance, let's find the actual time that it takes to go that distance. Now I want to do that over and over again for a whole bunch of different values of f0. So I'll have f0 this and f0 that, and look at the time it takes to go the given distance with all different gear ratios, and I can make a plot of that. And if God is good, this thing runs. God is having trouble doing the optimum. I don't know whether that means it's failing or whether it's just doing a bad job of it. I'll assume it just means it's not happy, but I'll be happy with the result. And I get out somewhere a plot. Where's my figure? Here, come here, figure. You see the figure? Plot f0 time. Did I make it go away when I didn't mean to? Anyway, I get a plot of the time it takes to go the given distance after it's done this fsolve. Somehow or other, those of you who got the homework done, got to some plot like this, which is this is showing gear ratio on the bottom and how long it takes to get the given distance. Most of you got there probably by guessing or doing complicated programs with complicated loops. But once things get complicated, it's probably easier to try to use this trick of encapsulating your knowledge so that each little bit of program doesn't involve anything too complicated. So each little bit of program is nothing too complicated. What's hard is to realize that you can trust yourself to go up in layers from one program to the next program. Any questions about what I said here? Of course, there's some weird things that you can't understand. It's not like you can possibly understand this syntax. This one you have to look up. Just like you can't possibly understand this syntax. By now, I remember it, but it's not like I understand it. It's just that's what the syntax is.
What does fsolve do?
fsolve finds a value of t that makes this quantity 0. The purpose of fsolve is to find roots of equations. And 10 there is an initial guess. So it says I'm trying to find t. I'm going to do it by using this function myError, which is a function of t. It better be, and a bunch of parameters. Here's a list of parameters that get passed, and here's the initial guess. That's the syntax.
Why are you calculating error?
The reason I call it error is because I want to find out how long it takes to go a given distance. The root finding program always wants to find 0. So I call this function myError, and the only difference between myError and the how far function is I subtract the actual distance I want to go, so they can try to find a t that makes that quantity 0. Root finding always tries to make some quantity 0. So if you want to make some quantity 37, you have to make a new function, which is the function you had, minus 37. Does that address your question? Okay, now to understand a program like this, you really have to have your hat on. That is all the separate pieces. You can't be insecure about it. So if you're just barely floundering on each piece, you can't put the pieces together because it's like putting a sentence together out of words that you don't quite know any of the words. Or a paragraph out of sentences where you don't quite know any sentences. To build up the structure, you have to have trust in the lower level words. Okay? Everybody happy? Thursday's guest lecture. Next Tuesday is me again. I will post the homework which is due the Tuesday after Thanksgiving. Brian is Friday.